today I did part of the lesson. I kept it short because the ninth graders were at the seminar. So I'm going to just fill you in on what you missed. So we're moving into chapter 5. We're going to work, the first, well, today and tomorrow we'll cover section 5.1 and 5.2. We're just getting into the introduction of a quadratic function, okay? So a quadratic function is different than a linear function for a few key reasons, but primarily when you're looking at the equation here in this rectangle, this is what dictates the quadratic function. And specifically, it's the x squared, x to the second power there. That exponent of 2 is what makes it quadratic. It's the largest positive exponent. So we call this the quadratic term in a quadratic function. And then over here, this is the next term right here, excuse me. What's going on here? This is the linear term. And then lastly, this is the constant, okay? So quadratics can be written in different forms, just like linear functions can be, right? You have standard form, you have slope-intercept form, and then point-slope form. So today we're going to be working in standard form and then what we call vertex form, which is this. It's not the equivalent, but it's similar to the point-slope form of a linear function. So standard form is slightly different than the standard form of a line. Basically, it's y equals, and then it's the quadratic term comes first, followed by the linear term, followed by the constant. Fractions and decimals are acceptable in standard form of a quadratic function, and that a value in the front there, that a value here can be a fraction, it can be negative, it can be a decimal. So that doesn't apply as it did in the standard form of a linear function. Okay, so a couple things. The a value can't be 0 in this situation, and that's mainly because if this term that's circled here is a 0, then it becomes a linear function, and it's got to be a quadratic function. Down below here, this is one example of a quadratic function, x squared, y equals x squared minus 6x plus 5. When we start looking at the graph of these, the standard graph of a quadratic function, it has this type of shape here. It's not a U, but it looks like a U. There's a critical point it has right here is a vertex. And this graph, it can be oriented opening up. It could also be oriented opening down. And then when we start studying parabolas, they can be oriented opening left and right there. Okay, so we're going to talk about how do we graph it, right? So from the get-go here, if you don't know how to graph any function, you just need to graph it. A table of values works every single time. It's a little dangerous in some cases in the sense that when we first started the table, the suggestion was to use -2 all the way down to +2. So we did that. We selected 5 values for x, and then what we did was we substituted those 5 values in to the rule for the function. Here's the work. You don't need to set this middle column up, but you can. It's a good way to organize. And then on the right column here, these are our y values, right? So these are our corresponding y values. The graph I'm using, I'm scaling by 2s right now. And just in this situation, I opted to not graph the point -2, 21 because I didn't have space. So we just dropped every other value in, right? So doing so, that leaves us with this value way up here. And then we have a y-intercept right here at 0, 5. And then we had, this is an x-intercept here at 1, 0. And then I think we got all the way down to about here, right? So those values we graphed. And from that, you can just see this is what we had, right? So just in green is what the values that we selected in our table gave us, which looks a little bit more like a line. It's not a line, right? Because the rate of change is not constant there. But that was an indication that, hey, we don't have enough points in our table. We know it's supposed to have this turn in it. So we just continue to add more points on the board, right? So then I started dropping more values in, right? So I got 3, -4. That is a critical point for us. This point here, 3, -4, is what we call the vertex. It's critical to have that. In this case, it's going to be our lowest point. And then we continue to populate our table. You can pull this up on the node outline, and we ended up with a few more points here in blue, right? So then we ended up with this point, and then this red point right there, okay? We also pointed out that we had the y-intercept here. Now the y-intercept is nice because you can see it right in the equation when it's in standard form. That +5, if you were to put 0 into the x's, you end up with a 5. That's your y-intercept, so that's nice. You can see that right away. Then it was noted that there is symmetry in this graph, right? So this red dotted line that's vertical that passes right through the vertex is a line of symmetry. It's not part of the graph, it's a characteristic of the graph. It's indicated with a dashed line here, and the equation for this line is the equation x equals the x coordinate of the vertex, so 3 in this case, right? Then we started talking about symmetry, right? So if you think about this, the distance from this red line right here to points on the curve right here, that distance right there, that runs from x equals 3 to x equals 6. It's a distance of 3. The symmetry also says that's a distance of 3. So if we had this y-intercept at 0, 5, then I can find this red point, which is what we're calling a symmetry point, symmetrical point, or reflection point. It's the same distance horizontally from the line of symmetry that that point is. And that's true for any 2 points on the curve. The distance is always common there. So you have one point, then you can map it to the other side of the line of symmetry there to find the other point. They're always going to be the same. And that's kind of what we got into with this. The only other thing I would point out is that there are x-intercepts here at the point 1, 0 and the point here at 5, 0. Not every quadratic function has an x-intercept though. If that graph were shifted up vertically above the x-axis, it will not have x-intercepts. Or if the vertex existed where it was and it was just flipped upside down, it's not going to pass the x-axis either. It's always going to have a y-intercept though. So that's kind of what we got into with just the intro of a quadratic function here.